Right now, somewhere around 20,000 light years from where you are sitting, there is a dead star spinning 707 times every single second, not per minute, per second. It weighs more than 2 of our suns compressed into a sphere you could drive across in about 15 minutes, and it is eating its companion alive, pulling matter off a smaller star one stream of superheated gas at a time, growing heavier with every orbit, spinning faster with every meal. That alone would be remarkable. But here is the part that keeps astrophysicists up at night. There is a mass limit for objects like this, a line in the physics that says, cross this and you stop being a star. You become a black hole. And this thing, PSR J0952-0607, is closer to that line than anything we have ever measured. We do not know exactly when it will cross. We do not know if it already has. And if it did, we would not find out for another 20,000 years because that is how long the light takes to reach us. But before we get to what happens when that limit breaks, we need to understand how something this extreme came to exist in the first place. Stay with me because this story gets stranger at every turn. Subscribe now if you want more stories like this because we are just getting started. Let's go back to where this story actually begins. Not with the pulsar itself, but with the moment humanity first realized that dead stars could still scream. On November 28, 1967, a graduate student named Jocelyn Bell Burnell was sifting through miles of paper chart recordings at Cambridge University. She had helped build the radio telescope herself, stringing together cables across a muddy English field, and buried in that data, she found something no one had ever seen before. A signal pulsing with the regularity of an atomic clock. Every 1.337 seconds, without deviation, a burst of radio waves arrived from deep space. The precision was so uncanny that her team half-jokingly labeled it LGM-1, Little Green Men, because what else could send a signal that perfect? Within weeks, Bell Burnell found a second source, then a third, then a fourth. And at that point, the alien hypothesis collapsed under its own weight because the odds of 4 separate civilizations all broadcasting with the same mechanical rhythm from different parts of the sky were essentially zero. What she had found was something far more extraordinary than aliens. She had discovered pulsars, the spinning remnants of dead stars, neutron stars so dense and so compact that they rotate at staggering speeds and sweep beams of radiation across space like cosmic lighthouses. That discovery changed everything we thought we knew about stellar death. Stars did not just fade out. They transformed into something new, something violent, something that could keep broadcasting across the galaxy for millions of years after the explosion that created them. And over the decades that followed, astronomers kept finding more of them. Faster ones, heavier ones, stranger ones, until eventually they found one that broke the models entirely. For decades, the physics of neutron stars seemed well understood. A massive star burns through its fuel, gravity wins the final battle, the core collapses, the outer layers explode in a supernova, and what remains is a ball of neutrons roughly 20 kilometers across. Dense, yes, a single teaspoon of neutron star material would weigh somewhere around 1 billion tons. That is more mass than every skyscraper in Manhattan stacked together, crushed into a space smaller than a sugar cube. If you dropped it onto the surface of Earth, it would not stop. It would punch through the crust, tear through the mantle, and keep falling until it hit the core. The gravity at the surface is around 200 billion times stronger than what you feel standing on the ground right now. But the model said there were limits. The Tolman-Oppenheimer-Volkoff limit, named after the physicist who calculated it, predicted that neutron stars should top out somewhere around 2 to 2.5 solar masses. Beyond that, the neutron degeneracy pressure, the quantum mechanical force that keeps the star from collapsing further, would not be enough. Gravity would win again, and the neutron star would become a black hole. Then in 2017, a team using the LOFAR radio telescope in the Netherlands discovered PSR J0952-0607 in the constellation Sextans. It was spinning at 707 revolutions per second. That alone made it the fastest spinning neutron star in the disk of the Milky Way. Its surface was moving at a significant fraction of the speed of light. If you could somehow stand on the equator of this thing, which you could not, because you would be instantly crushed into a layer of atoms thinner than a sheet of paper, you would be whipping around at roughly 20% the speed of light. But the real surprise came in 2022, when Roger Romani and his team at Stanford University used the Keck 1 telescope in Hawaii to measure its mass. The result, published in the Astrophysical Journal Letters, 2.35 solar masses plus or minus 0.17. The heaviest neutron star ever reliably measured, not slightly above average, not modestly exceeding expectations, right up against the theoretical ceiling. The gap between this pulsar and the point of no return was terrifyingly small. Now stop and sit with that for a second. But here is the part of this that stops being abstract and starts being personal. Why should you care about a dead star 20,000 light years away that is slightly too heavy? Because the physics that governs what happens inside PSR J0952-0607 is the same physics that determines what happens to matter everywhere in the universe, including the matter inside your body. Neutron stars are the most extreme laboratories in existence. The pressures inside their cores are so immense that we genuinely do not know what state matter takes at those depths. It could be a superfluid of neutrons, it could be a quark soup where even the neutrons themselves have broken apart. Understanding where the mass limit actually falls tells us something fundamental about how the universe is built at its most basic level. We do not yet know exactly what it means that a neutron star can reach 2.35 solar masses and survive. But the fact that we now have to stretch our models to accommodate it is itself a shift in how we understand the most extreme conditions matter can endure. And that brings us to how this pulsar got so heavy in the first place, because it did not start this way. PSR J0952-0607 was born in a supernova like every other neutron star. It probably started its life at around 1.4 solar masses, the standard birth weight for these objects. So where did the extra mass come from? The answer is its companion. Orbiting this pulsar, completing a full loop every 6.4 hours, is the fading remnant of what used to be a normal star. It has been stripped down to less than 20 times the mass of Jupiter. It is barely a star anymore. What happened is a process astronomers call recycling. The companion's outer layers are caught in the pulsar's gravitational grip. Matter streams off the smaller star in a searing arc of superheated plasma, spiraling inward, forming a glowing accretion disk around the pulsar. Some of that material falls onto the surface. Each gram adds mass. Each gram adds angular momentum. The pulsar spins faster, it grows heavier, and the companion shrinks. This is why they call it a black widow pulsar. Like the spider, it consumes its partner, not in a single act of violence, but slowly, atom by atom, orbit by orbit, over hundreds of millions of years. Roger Romani and his colleague Alex Filipenko at the University of California, Berkeley, turned the Keck 1 telescope on this system 6 times over 4 years. Each observation was a 15-minute window timed to catch the companion at specific points in its orbit. The companion is so faint, so thoroughly consumed, that detecting it at all required one of the most powerful telescopes on Earth. And yet from those thin slivers of light, they were able to calculate the pulsar's mass with enough precision to make a definitive claim. This is the heaviest neutron star ever found. If you are the kind of person who finds this as strange and fascinating as I did while researching it, drop a comment letting me know, because it genuinely helps me figure out what other space stories are worth covering next. But here is where the story takes a darker turn. Remember the Tolman-Oppenheimer-Volkoff limit, the boundary that separates neutron stars from black holes. Current estimates place it somewhere between 2.0 and 3.0 solar masses, depending on the equation of state for nuclear matter, a parameter that physicists are still debating. PSR J0952-0607 at 2.35 solar masses is already well past many of the stricter theoretical predictions, and it is still feeding. The companion is still losing mass, the accretion disk is still delivering material. Every orbit, the pulsar gets a little heavier, a little closer to the edge, and here is the detail that tends to stop people in their tracks. Unlike a supernova, which announces itself with an explosion visible across galaxies, a neutron star collapsing into a black hole would be almost silent. The pulses would simply stop. The radio signal that has been sweeping past our detectors like clockwork would just vanish. One moment, a lighthouse. The next, darkness. No shockwave, no blinding flash. Just a sudden absence where a signal used to be, and in that silence, an event horizon forms. Space warps. Light bends inward and cannot escape. What was once the densest visible object in the universe becomes the densest invisible one. Astronomers have never witnessed this happening in real time. No one has ever caught the moment a neutron star crosses that threshold and disappears, but the gravitational wave detectors LIGO and Virgo are specifically designed to detect the kind of ripple in space-time that such a collapse would produce. If PSR J0952-0607 collapsed tomorrow, or if it collapsed 20,000 years ago and the signal is already traveling toward us, those detectors might catch the signature. It would be the first direct observation of a pulsar dying its second death, a scientific milestone built on a cosmic funeral. But pulsars are not the only breed of neutron star that commands attention. There is another kind, one that does not need to spin at 707 times per second to be dangerous, one that does not need to steal mass from a companion. It just sits there, quiet, unassuming, until the pressure beneath its surface becomes too much to contain. It is called a magnetar. Take everything about a neutron star, the crushing gravity, the impossible density, the compressed atomic matter, and now add a magnetic field so intense that it does not just push particles around. It dismantles them. A typical refrigerator magnet produces a field of about 50 Gauss. The Earth's magnetic field is about half a Gauss. A standard hospital MRI machine operates at around 10,000 to 30,000 Gauss. A magnetar's field reaches up to 1 quadrillion Gauss. That is 1,000 trillion times the strength of Earth's field. At that intensity, the magnetic force does not just deflect charged particles. It physically reshapes atomic structure. The electron orbits around atoms become elongated into thin cylinders. Chemistry itself stops working. If you were within a few hundred kilometers of a magnetar, the atoms in your body would be ripped apart not by heat, not by radiation, but by raw magnetic geometry. And on December 27, 2004, a magnetar called SGR 1806-20, located roughly 50,000 light-years away in the constellation Sagittarius, proved exactly how violent these objects can be. It released a burst of gamma radiation so powerful that it saturated the detectors on multiple orbiting satellites. The energy pulse was so intense it measurably disturbed Earth's ionosphere, causing disruptions in radio communications on the planet's surface, from 50,000 light-years away. For a fraction of a second, that single magnetar outshone every other X-ray source in the sky combined. Scientists believe the burst was triggered by a starquake, a fracture in the magnetar's ultra-dense crust caused by the unbearable tension of its own magnetic field. The crust shifts, the field realigns, and the energy released in that single crack makes our most powerful nuclear weapons look trivial by comparison. The closest known magnetar sits about 8,000 light-years from Earth, far enough that even a major flare would not seriously threaten our planet. But calculations published by Adrian Malott and Brian Thomas at the University of Kansas suggest that a gamma ray burst from a source within about 6,000 light-years could strip away significant portions of our ozone layer, exposing the surface to lethal levels of ultraviolet radiation from the sun. Their research, published in the International Journal of Astrobiology, proposed that such an event may have contributed to the late Ordovician mass extinction roughly 440 million years ago, one of the 5 great extinction events in Earth's history. Now let's talk about what is happening right now in 2026. PSR J0952-0607 is still spinning, still feeding, still pulsing its signal across the galaxy at 707 beats per second. Romani's team confirmed its record-breaking mass with refined measurements published in the Astrophysical Journal in early 2025, tightening the uncertainty to 2.35 plus or minus 0.11 solar masses. The companion continues to lose mass, the accretion disk continues to glow, and the pulsar continues to creep, gram by gram, toward a boundary that no neutron star has ever been observed to cross. Meanwhile, our detection capabilities are improving. LIGO and its partner observatories have been upgraded to greater sensitivity. If a neutron star collapse generates gravitational waves anywhere in our galaxy within the detection range, we now have a real chance of catching it. The window to observe PSR J0952-0607 as a neutron star is finite. It will not spin forever, it will not feed forever. Someday, possibly in 1,000 years, possibly in 10 million, the balance will break. And when it does, the fastest, heaviest neutron star we have ever found will vanish. Not in an explosion, not in a flash, in silence. Here is what I want you to take away from all of this. We live next to a quiet, stable, middle-aged yellow star that has been burning steadily for 4.5 billion years. Our magnetic field is gentle, our atmosphere is breathable, our orbit is calm, and it is easy to look up at the night sky and assume that the universe operates with the same kind of gentle predictability. It does not. Out there right now, dead stars are spinning faster than any engine humanity has ever built. Crushed matter is pressing against the limits of physics itself. Magnetic fields are tearing atoms into geometries that have no name in any chemistry textbook. And one particular object, a tiny sphere no wider than a city, is balancing on a razor's edge between 2 of the most extreme states matter can occupy, a neutron star and a black hole. What separates one from the other might be a few tenths of a solar mass, a few more orbits, a few more stolen atoms from a dying companion. The universe did not build PSR J0952-0607 to impress us. It built it because physics allows it, because gravity and spin and pressure and quantum mechanics converge into something that should not exist but does, still spinning, still feeding, still holding itself together by the thinnest margin the cosmos permits. One dead star, 20 kilometers wide, defying its own destruction 707 times every second. If this is the kind of story that makes you want to understand what else is out there, subscribe and turn on notifications because there are more stories like this waiting to be told. Drop a comment with the part that surprised you the most, whether it was the mass limit, the magnetar flare, or the silence of a collapsing star. And share this with someone who deserves to know just how strange the universe actually is, because this story deserves more than the silence it is getting.